Hi, and welcome to the last part of the tutorial on real and functional analysis for machine learning. And here we'll cover inner product spaces. Now, an inner product space is a pair F and these angular brackets, where F is a vector space and these angular brackets are what is called an inner product. Now, an inner product is just a real valued function, right? So what do I mean by that? I mean that actually we could write this is just a function that takes two arguments f and g and gives you a real value, right? But this notation is really tedious, so we just write f comma g to denote the inner product. Now, such a real valued function is an inner product only if it satisfies the following four properties. The first one is, in some sense, commutativity, or rather, when this function takes an arguments f and g, it returns the same value when the function takes an arguments g and f. Similarly, when the function is given both its arguments as the same vector, then I always get a non-negative quantity, and I get 0 if and only if the vector, both the vectors there were 0. The third one is a linearity of the dot product over addition, and that can be written in the following fashion. So f plus g dot h is fh plus gh. And the last one is if I multiply by a scalar c, then it doesn't matter whether I multiply the first vector or the second vector, or if I first evaluate this real valued function over its arguments f and g and then multiply that real value by the scalar c. Great. Let us actually look at some examples to make things clearer. Now, the first example is one that you might be familiar with already. It is the inner product space where the vector space is Rn and the inner product is defined as x transpose y, where this is the linear algebraic notation for transpose. It is the sum of I equal to 1 to n xi yi. So here x and y are both treated as n-dimensional column vectors. So I have two column vectors and I take the transpose of the first times the second. Now this is the usual Euclidean dot product, it's called, and sometimes we just call the inner product space Rn if the inner product is assumed to be the usual Euclidean inner product. Then we just say that the space we are working with is Rn, but you must understand that implicitly we are assuming that there is an inner product defined and it's the usual standard definition of the inner product. Now one can define on Rn a different inner product. So here's a different one with a subscript A, and that A represents a symmetric positive semi-definite matrix A. So if you're unfamiliar with what a PSD matrix is, then I recommend looking at some linear algebra tutorials. But if we were to take a PSD matrix A, then we can define a different dot product x dot y subscript A, and we can define this dot product to be x transpose ay. And if you expand that out, it is the dot product is just the summation of I equal to 1 to n, j equal to 1 to n, aij, xi, yj. Now note that both x and y have to be members of Rn. It doesn't make any sense to take the dot product between x and y when they are of different spaces. And since both of them are in Rn, A has to be an n cross n positive semi-definite matrix. So here we have, in this case, the same space Rn, but now associated with a different dot product. You can verify that this function, that takes two arguments and returns this value, is actually a valid dot product in the sense that it satisfies the four properties that we just introduced. Here are a few more different examples. We're already familiar with the space little l2, and this is the space of all square summable sequences that we saw earlier. And here we can define an inner product. So this is really a definition, right? So we define the inner product between two such sequences to be the infinite sum of xi, yi. Next, we look at functions like we already saw what capital L2 is. It's the set of all square integrable functions. and we can define a dot product f dot g. This is the canonical dot product, and it's defined as the integral from minus infinity to infinity of f of t g of t dt. Now, often when this is the dot product that is understood to be the case, then we'll just write L2 or maybe little L2 in this case when we're using the canonical dot product. But as we have said multiple times now, you can choose a different dot product. And an example of that could be when you take minus infinity to infinity f of t, g of t, p of t dt for some probability distribution p. Okay, so that would actually result in a different dot product, and in that case we don't just write L2, we might write something like L2 of p or something like that to indicate that it's associated with a different dot product. It's the same space, it's a similar set of functions that are square integrable, but with respect to a probability distribution p. Lastly, let's look at the example of m cross n matrices. We can define a dot product over matrices. So the dot product between two matrices is defined as the trace of A transpose B. And if one was to expand that out, it turns out that it's the sum over the indices I from 1 to n and j from 1 to m of Aij, Bij. So it's just as if I took two matrices and I multiplied the first element by the first element, the second element by the second element, and so on till the last element by the last element. And these could be m cross n matrices. And one can check that this is actually a valid definition for a dot product in the sense that this function of two matrices satisfies the four properties on the previous page. And it actually just behaves very similar to the vector dot product. It's as if you took the matrix and you strung it out as a long vector, and you took the Euclidean dot product of those two vectors. Now, an important point is that an inner product automatically induces a norm which induces a metric. So if I give you an inner product space, so you're not allowed to choose it anymore, so I fix it for the moment, where f is some fixed vector space and this is some fixed inner product that was already given to you, then one can define an associated norm where the norm of f is just the square root of f dot f according to this definition of dot product. And as we saw earlier, whenever you have a norm, it gives rise to a metric. And so the metric, the distance between f and g, can be defined as the norm of f minus g. So often when we're talking of Rn, the n-dimensional vector spaces, we often associate it with the usual Euclidean inner product, and that gives rise to the usual L2 norm, and it gives rise to the usual Euclidean distance between two vectors. But it's important to remember that that this is just one choice of inner product, one resulting norm and one resulting distance. And in fact, on the same space, I can associate different norms. So we already saw, for example, the L1 norm, which gives rise to the L1 distance between points. And there are other dot products like the Mahalanobis dot product, which had the matrix A that we introduced on the previous page. So when one usually works with Rn, if it's unsaid, then it's the Euclidean dot product, the Euclidean distance, and the Euclidean norm and the Euclidean distance. But it doesn't have to be the case, and one can associate different norms with those vectors and different metrics with those vectors. Now, the Cauchy-Schwarz inequality, or sometimes called the Cauchy-Schwarz-Bunyakovsky inequality, is really important. It says that for any valid dot product, so you fix your choice of dot product, it has an associated norm, as we saw above, which satisfied the following inequality. And it says that f dot g in absolute value, f dot g is at most the norm of f times the norm of g. This is a really crucial inequality, and it will be interesting to try and write down this inequality for all the examples that we saw on the previous page. Remember that the vector space we're dealing with could be function spaces. So then in the case of functions, what this would say is, one example of such a statement is that integral from minus infinity to infinity of f of t, g of t, dt, right? So that's the left hand side, the absolute value, is at most the square root of integral from minus infinity to infinity f of t squared dt, which is the norm of f, times the square root of the integral, again from minus infinity to infinity, of g of t squared dt, which is the norm of g. Right? Again, the limits are the same. And that's what the Cauchy-Schwarz inequality would say if the dot product we chose over capital L2 was this dot product, it would give rise to these norms. And then this is what the Cauchy-Schwarz inequality would say. And it would be instructive to write down what the associated norms are for this, for the spaces we saw earlier. Let's end with the discussion of a crucial concept called the orthonormal basis. Right? So for any inner product space X and the inner product given by those brackets, an orthogonal system is a set of vectors, which could be infinite, but this set of vectors such that any two vectors, if I take their dot product, is 0, as long as those vectors are different. Now the system is orthonormal is not only if every pair of vectors is orthogonal, but the same vector, if I take a dot product with itself, then the dot product is 1. So it's a unit norm. And lastly, the system is a basis if that set of vectors spans the entire space. Now, an inner product space can have many different orthonormal bases, the same inner product space. So for example, for R3, when given the usual Euclidean inner product, 1, 0, 0, 0, 1, 0, and 0, 0, 1 form an orthonormal basis. You can easily make out that they're orthogonal to each other and they're unit norm and that they span R3. But here's a different orthonormal basis. It's 1 by root 2, 1 by root 2, 0, minus 1 by root 2, 1 by root 2, 0, and 0, 0, 1. And you can again verify the same properties hold, that they're orthogonal, unit norm, and that they span R3. Here's a different space. This is L2. Again, I'm not writing the dot product because I'm associating it with the typical Euclidean dot product. And in that case, sine of alpha transpose x plus beta, where alpha and beta are in the reals. So there are uncountably infinitely many such functions. That this is actually a basis for L2. We're going to look at more, think about bases and spans and things like that much more when we look at the SVD. But it's important to note that we can't talk about the notion of orthogonality and bases without introducing an inner product space. And the set of bases that you come up with will depend on your notion of dot product, because two vectors can be orthogonal for one notion of dot product and not orthogonal for a different notion of dot product. So that's all for the moment. I think we've finished all these topics, and we shall continue with the next set of tutorials on the SVD. Thank you.